Hi, I'm Yiru. In this talk, I'm going to present our work, Domain Adaptation for Eye Segmentation. This work is produced by eye tracking team from Facebook Reality Labs. Eye tracking is a critical field in the AR/VR community to capture and understand eye states. We need to develop robust eye tracking models for real-world applications which can reliably work under all environmental conditions, across different hardware configurations, and work for all individuals. Recently, machine learning has been used to apply to various eye tracking applications. For example, in gaze tracking, we need to take eye images as input and train a segmentation network to produce the masks. Later on, a geometric model is used to map the masks to estimate gaze. In this case, we need a large amount of data and the corresponding annotations to train the eye segmentation network. However, data annotation is labor-expensive and time-consuming, especially for segmentation tasks where each pixel needs to be labeled. Therefore, domain adaptation has been applied to ease the problem of data annotation. Domain adaptation is the ability to apply a model trained in one source domain to a different but related target domain. Usually, we have one source domain where the quantity of data is usually large and the quality of annotations is guaranteed. And we have a target domain where quantity and quality of annotations is limited. In this work, we use OpenEyes as a source domain data, which are collected in a lab-controlled setting. We collect eye images using a VR head-mounted device as a target domain data. As you can see, the varying illumination introduces challenges in the data, and quality of annotation is not guaranteed. For example, the corners of sclera is not captured in annotations. However, domain adaptation can't be naively used due to domain gaps between source and target. Here, we show an example of segmentation prediction from model which is trained on source domain data and applied on target domain. It's clearly that the poor performance is due to the domain gap between source and target data. Therefore, we need to carefully design the pipeline to drive the two distributions closer. Here, I'd like to mention the notations and goals of our work. In domain adaptation, three frameworks are mainly studied. Unsupervised domain adaptation, short for UDA, applies this for cases where no annotations are available in target domain. Supervised domain adaptation, short for SDA, is applied when limited label target data are available. And in semi-supervised domain adaptation, short for SSDA, in addition to a small amount of labeled target data, a big chunk of unlabeled data is available. We believe SSDA is more suitable for real-world scenarios, and in this work, we investigate SSDA by asking the following questions. Given a fixed annotation budget, how much data needs to be labeled to reach a reasonable performance on target domain? We systematically compare UDA, SDA, and SSDA performance as a function of the number of available target data during training. The second question is how to optimally utilize unlabeled data. We explore the semi-supervised learning to maximally leverage the information from unlabeled target data. Our pipeline consists of two subnetworks, a segmentation network and a discriminator. The discriminator is a fully convolutional neural network which takes probability maps from segmentation network and outputs a confidence map. This map indicates how confident the discriminator about each pixel in the image belonging to source or target domain. Here, we show the loss functions for these three frameworks. I'm not going too detailed, and please refer to the paper for more information. A bit more would be talked on how to utilize the unlabeled target images to improve segmentation performance. Specifically, a semi-supervised loss is designed by generating pseudo-labels for eye regions in the unlabeled target images. The discriminator generates confidence score for each pixel in the image belonging to the source or the target domain. Only the pseudo-labels of regions where the confidence score is above a threshold is used to train the segmentation network via a masked cross-entropy loss. Here comes the results. As mentioned before, we aim to investigate how the performance on segmentation is impacted by varying amounts of target domain data during training. Here, we show the performance of UDA, SDA, and SSDA trained with varying amounts of target data. We note that the mean intersection of union increase and reach a plateau as more target data are available, and the extent of increase is much smaller for model trained under UDA. With only 200 labeled target images, mean intersection of union is improved by 5.4% and 6.6% from UDA to SDA and SSDA, respectively. It affirms our hypothesis that, even with limited number of labeled target data, domain-specific information can boost the performance. SSDA consistently outperforms SDA, since it's able to leverage the most available information. The gain in the performance for SSDA relative to SDA is brought about by the addition of adversarial loss and the semi-supervised loss from unlabeled target data. However, since we have a fixed amount of target data, and in SSDA, as more target data with annotations are provided, the amount of unlabeled data is decreased. Therefore, the performance gain brought from unlabeled data is diminishing. This explains the smaller performance gap between SDA and SSDA as more labeled target data are available. Also note that SSDA is able to achieve a competitive of 89.5 with a round of only 50 of the data being used. It is encouraging to observe that the proposed SSDA can efficiently take advantage of insufficient labels while still producing competitive performance. We summarize the performance for the case when all the labeled target data are used. Note that the lowest accuracy is from sclera. However, for many eye tracking applications such as gaze estimation, more focus is on high accurate pupil segmentation, where SSDA could deliver up to 90% accuracy. Finally, we show some visualizations. Note the labels in target domain are missing fine-grained boundaries, such as detailed boundaries of sclera. Domain adaptation is able to transfer the knowledge from source domain with high-quality labels to target domain to improve segmenting detailed geometry, such as sclera, in the targeted images. We also show the Tisney visualization of 3 frameworks. Qualitative results show that with domain adaptation applied, the distributions of source and target domain overlap closely. As a takeaway, we consider the problem of domain adaptation for eye segmentation under the setting where a small amount of labeled images and a majority of unlabeled images in the target domain are available. We systematically compare the performance of eye segmentation models using UDA, SDA, and SSDA as a function of the number of labeled target data. Results demonstrate the benefit to annotate a small number of target domain data to effectively perform domain adaptation using SSDA. In our future work, we plan to explore what aspects of eye tracking data quality are affected by segmentation of paraocular regions.